So another skill that we've developed in this past unit is using mental mathematics, using our knowledge of graphs to get our way through some of these limit questions. That's going to be especially helpful when, for whatever reason, you cannot plug it in. You cannot plug infinity into the function. So what we do is instead we have some conversation and we say, well, x is approaching infinity. Well, what happens to that x? If whatever x is, I plug it into this function, I'm supposed to square the x. Well, if x is approaching infinity, certainly x squared is approaching infinity even faster. If I then add 6 to that, that is approaching infinity. But what I need to do at the end is I have the limit as x approaches infinity of 1 divided by x squared plus 6. So what happens to the expression 1 over x squared plus 6 as the denominator gets bigger? As that denominator approaches infinity, 1 divided by an increasing number is 0. We're approaching 0. Let's go through that one more time. The limit as x approaches infinity of this function, we sort of mentally say what happens as x approaches infinity. As x approaches infinity, x squared gets even bigger. Add 6 to that, it's even bigger still. But 1 divided by a really, really big number is equal to 0. That's what you need to do. Some of you are able to do that level of analysis in your head without writing it down. That's fine. That's great. If the notation helps, let's apply that notation. All right, next problem. H is approaching 0. Limit as h approaches 0, cosine of 1 divided by h. Well, let's see. As h approaches 0, 1 over h is going to get closer to either positive infinity or it's going to get closer to negative infinity. What I know about the cosine graph is this. It starts here at the point 0, 1. It decreases and then it increases, and then it decreases and it increases. That continues to happen as we head out towards negative infinity as well. As h approaches 0, 1 over h is approaching either positive infinity or negative infinity. But the cosine of something that's getting bigger, as I head out on the cosine off to infinity, what happens, it's that oscillation. So we would say that the limit does not exist because of oscillation. O-S-C-I-L-L-A-T-I-O-N. Done. Last one, a little bit trickier. Now we're bringing in parameters. We have k. We're told that k is greater than 0. And now we need to find the limit as x approaches negative infinity of a, don't even know what a is, times e to the kx power. What you learned in Algebra 2 or in pre-calculus is that exponentials have this form, that they are increasing from left to right if you have e being raised to the kx power where k is greater than 0. If the k is a negative value, it would be decreasing. It would be a decay problem. That would be the graph of y equals e to the kx, where k is less than 0. Since we're told that k is positive, it's this top one that we want. So what happens? As x approaches negative infinity, well, what happens to the graph of e to the kx? As x approaches negative infinity, we see the graph decreases and decreases and decreases, getting closer to 0. Whatever a is, a times something that gets closer and closer to 0 will also approach 0. So we can say with confidence now that the limit as x approaches negative infinity of a times e to the kx is equal to 0. Those are 3 great examples of how you can use your knowledge of graphs or your number sense skills to solve some of these tricky limit questions. Okay, so now that we have limits under control and we've got some good video to look at, we're going to turn our attention to horizontal and vertical asymptotes. These are things that you've been exposed to back in Algebra 2 as well as in pre-calculus. I would expect that if you were given this graph, you'd see that the graph appears to get closer to the horizontal line y equals 0 as we head off towards infinity and negative infinity. It appears that the function, as we get closer to 2, heads down towards negative infinity and heads up towards positive infinity. We would say that you have a vertical asymptote at x equals 2. As you approach negative 2 from the left, the graph heads off to positive infinity. As you approach negative 2 from the right, the graph heads down towards negative infinity. So we have a vertical asymptote at x equals negative 2 and a vertical asymptote at x equals positive 2. Well, let's go through and have some calculus conversation about this. Let's prove why these things are the way that they are. What we want to find out is what happens to the function as x approaches infinity. It looks like the graph is getting closer to 0 as the x values head off to infinity. But let's look at the y. Let's find the limit as x approaches infinity of this function. We can't plug in infinity, but we can say that as x approaches infinity, x squared is going to approach infinity. X squared minus 4 then must approach infinity. And 1 over x squared minus 4 approaches 0. So I can track it through with the calculus. The limit as x approaches infinity of this rational expression is equal to 0. So that implies that we have a horizontal asymptote at y equals 0. Great. That's the calculus defense for why you have a horizontal asymptote. That also means that if you don't have access to the graph and all you have is this rational expression, you can use your knowledge of calculus to find the horizontal asymptote. What we also want to do, and I don't think I've emphasized this enough in class, is we pay attention to what happens on both ends of the graph. Over here on the right and over here on the left. So let's run through that quickly. As x approaches negative infinity, x squared is going to approach positive infinity. X squared minus 4 approaches positive infinity. And 1 over x squared minus 4 approaches 0. So, yeah, we already have that information. We have a horizontal asymptote at y equals 0. It is possible, and you will see an example in just a little bit, of a graph that has 2 horizontal asymptotes. As we head off towards infinity, one thing happens. As you head off towards negative infinity, something else happens. Let's turn our attention to the vertical asymptotes. I have a vertical asymptote at x equals 2. Well, why? What we have is that if I take the limit as x approaches 2 from the left of 1 over x squared minus 4, I can see from my graph, that as x approaches 2 from the left, the y values head off towards infinity. Let's go through and do the calculus to verify this. So, as x approaches 2 from the left, that means x squared, if x is just a little bit less than 2, x squared will be just a little bit less than 4. That means that x squared minus 4 will be just a little bit less than 0. You take 1 and divide it by something that is just a little bit less than 0, and that is going to approach negative infinity. I did something wrong there, didn't I? No, I didn't do anything wrong, sorry. Limit as x approaches 2 from the left is negative infinity. If I look at the graph, as x approaches 2 from the left, the graph is heading down towards negative infinity. I'm running out of space here, but you could go through the same logic and say, all right, well, as x approaches 2 from the right, so numbers just a little bit bigger than 2, x squared is a little bit bigger than 4. X squared minus 4 is going to be just a little bit bigger than 0. 1 over x squared minus 4 is going to get closer to positive infinity. That is what's happening over here. As x gets closer to 2 from the right, the graph heads off towards positive infinity. Having either one of these things happen means that I have a vertical asymptote at x equals 2. I could go through, do that same analysis again for x equals negative 2, and I'm going to leave that to you all to do that at home. Let's try another one.